Picture two small glass vials, both containing a fine white powder. To the naked eye, they look completely identical. One might be a harmless compound, like salicylic acid, and the other could be something highly reactive. Figuring out which is the core challenge of organic chemistry lab work. Before we can begin testing these unknown organic powders, we have to establish strict safety baselines. This reference guide displays universal hazard symbols. You need to know exactly what you are handling, whether a compound carries a harmful, toxic, or flammable warning. We also have to prevent physical hazards during the testing process itself. If you heat a liquid too quickly, it can reach a superheated state above its boiling point and violently vaporize. This sudden eruption is called bumping. We prevent it by stirring continuously or adding boiling stones to ensure a steady heat distribution. Once it is safe to proceed, we establish our baseline by finding the concom's pure melting point. This is the exact temperature where solid and liquid phases reach equilibrium at 1 atmosphere of pressure. A pure solid has a sharp transition, melting entirely within a very narrow range of 0.5 degree to 1 degree Celsius. Because human eyes are easily deceived by identical white powders, we cannot rely on appearances. Measuring precise physical constants is the most reliable way to begin identifying organic matter. This diagram illustrates the melting point apparatus, consisting of an oil-filled flask, thermometer, and burner. The tube is attached closely to the thermometer. To ensure accurate readings, the bulb must sit exactly 1 centimeter above the flask's bottom. Getting accurate data requires strict preparation. First, the solid is ground to a fine powder and packed into a tiny capillary tube. The powder must be densely packed to a height of exactly 2 to 3 millimeters. If the sample is too thick, the heat won't penetrate evenly, and your melting range will artificially broaden. The most common point of failure happens next. If you turn the burner up too high, the oil heats faster than the glass can transfer that heat to the thermometer. To avoid this lag, you must monitor the bath and maintain a strict, constant heating rate of 2 to 3 degrees per minute. Achieving an accurate, authentic physical constant relies entirely on your mechanical precision during setup and your patience while heating the apparatus. These graphs show how impurities alter phase transitions. On the left, the dashed line shows an impurity reducing vapor pressure, which lowers the melting point. On the right, as the impurity percentage increases in a mixture, the melting point follows this sharp curve downward. Let's apply this in practice. Suppose you have an unknown powder that melts sharply at 120 degrees Celsius. You mix it with a known sample of benzoic acid, which also melts precisely at 120 degrees. When you test this new mixture, it slowly melts over a broad range, from roughly 103 to 111 degrees. What does this tell us? Because the melting point dropped and the range broadened, we know the two compounds are different. Even though they share the exact same individual melting point, when combined, each behaves as a structural impurity to the other. Impurities act as physical disruptors in a crystal lattice. By forcing two unknown samples to melt together, you disrupt that lattice, providing clear proof of their chemical non-identity. Physical testing is an excellent way to narrow the field, but it has limits. To differentiate complex liquid unknowns, like aldehydes and ketones, chemists must move beyond physical traits and force specific chemical reactions. This comparison table maps out the expected reactions for aldehydes and ketones. We start with the 2,4-DNP test. This acts as a broad net that catches all carbonyl groups. As you can see in the top row, both aldehydes and ketones react the exact same way, yielding a yellow, orange, or red precipitate. To actually tell them apart, we need a more targeted approach. Toland's reagent is highly specific. When we apply it, ketones show no reaction at all. Aldehydes, however, undergo a reaction that deposits a highly visible silver mirror on the inside of the test tube. We confirm this differentiation using Fehling solution. Just like before, the ketone ignores the reagent. The aldehyde reacts clearly, dropping out of solution as a brick red precipitate. Absolute certainty in organic chemistry requires this methodical approach. You build a layered defense, first establishing physical baselines to rule out imposters, and then deploying targeted chemical tests to reveal a molecule's true identity.